However, methodological factors aside, there are a number of just perhaps cause and effect relationships to take into a case. So, and these are quite important because when we look at these, they have a potential to cause strife in terms of our understanding. Because if we think about this very, very logically, one would argue, and absolutely should argue physiologically, that there should be a cause and effect relationship. In other words, if you identify lactate turn points, the transition in terms of lactate, the sudden acceleration in lactate, if you identify that point correctly, then that point should always occur because the physiology holds at the same point as the gas exchange threshold. But there are these kind of contrary studies that are often bandied around as means of kind of suggesting, well, this is not the case. And the first one that's used is a study by Hagberg. And Hagberg observed a distinct ventilatory threshold in patients suffering from a cardinal syndrome. Now, these patients lack the enzyme phosphorylase. They have an inability to produce lactate. But what they found is in this patient group, they didn't get a lactate response, but they got a ventilatory threshold response. So how is that possible? Well, critics of the gas exchange threshold and critics of this kind of area of physiology will say, well, this demonstrates that these two are not coupled. It doesn't. Remember that fundamentally, the gas exchange threshold, it reflects that second source of CO2. Where is it coming from? Remember that we showed it's hydrogen ions. So although these participants don't necessarily have a lactate response, they still have a hydrogen ion response. Remember that hydrogen ions are produced from metabolism. You get hydrogen ions as the product of the TCA cycle. They will still produce those. The fact they don't have the enzyme phosphorylase and therefore they don't have the ability to produce lactate is almost irrespective. So it's a bit of a red herring when this is often postulated. Study in 1983, Simon compared trained cyclists to untrained cyclists, and they said, well, the VT, they called it, which is gas exchange threshold, and LT2 occurred at the same workload in the trained, but not in the untrained. Well, why might that be the case? Well, almost certainly it goes back to what Paul was referring to in the previous slide, which is it's methodological. If you are adopting the same workloads in trained and untrained as they did in this protocol, then the untrained are going to actually produce less reliable results because the increases are either are almost certainly too intense for them to produce, and you end up missing the response, particularly when you're using Douglas bag based data. So if you've got a trained runner, as we've got on the treadmill, this is in our lab here, if you've got a trained runner on the treadmill and they have an increase in speed of, let's say, 1 kilometre an hour every 3 minutes, and then you use an untrained individual and you do 1 kilometre an hour 3 minutes, it's a much bigger metabolic increase for the untrained than it is for the trained. Therefore, you're less likely to be able to identify the gas exchange threshold in those individuals because you'll have missed it. And then the last one that's often cited is some work from Glenn Gazer and Dave Paul. This is Dave Paul's actual, I think it was his PhD or postdoc work back in 86, I think it's PhD. And they observed a significant increase in VO2 max following 3 weeks of training alongside an increase in the workload associated with LT2. So they found that both increased with training in just 3 weeks, but they found no change in gas exchange threshold. Same thing applies. They were only using one method. They used V-slope to identify gas exchange threshold. They didn't have the knowledge that Gaskell has brought forward now, which is actually corroborate the gas exchange threshold with V-slope and the ventilatory equivalents to identify it and then compare those to LT2. It is much harder to identify than perhaps the graphs in this session would suggest. And any means that you have to be able to corroborate the finding is going to be really, really important. So there is a cause and effect relationship, but I think it was important to explain why studies sometimes suggest there isn't, and actually just understanding the kind of the background physiology or the background methodology to those studies. And so actually when we look at the data, this is from the data from Gazer and Poole. Here we've got the pre-training group. So this is the lactate. This is the VO2 at the lactate turn point, and then the percentage of VO2 max. So what we can see is the VO2 increases, sorry, the percentage of VO2 max increases with training, as one would expect. But their argument is, well, actually, the percentage of VO2 max for, they've called it ventilatory threshold, which is the gas exchange threshold, didn't really change at all. Don't be fooled by the numbers going down. There's no significant difference in the data. Well, almost certainly, as I say, it's a methodological thing. They're saying there's a disparity in the time course of adaptation. Well, that may well be, you know, a factor at play here, but it doesn't explain if they are linked physiologically. It doesn't explain why this parameter is increased and this hasn't. Now, which is correct? Is it that they've misidentified this, or is it they've misidentified this? And of course, we'll never really know. Remembering that the lactate that you're taking is fundamentally a function of the workload at which you record it at. If you've got VO2 in a breath-by-breath data set, you're continually recording it throughout. In Douglas bags, it's slightly different. You take a VO2 at each stage, so you'll never quite know which is the kind of the misnomer in terms of the data here. It could be that the lactate is just misleading because it's just being taken at the increments that they've used. It could be that the VO2 or the ventilatory responses are misleading as well. Either way, it's almost certainly a methodological response rather than a physiological response that we get in the data. And here we've got some blood lactate and ventilatory-based parameters. This is from Andy Jones and Joe Doust. And it's primarily, they were looking at the lactate minimum test. That's not really what we're perhaps worried about here. But what you can see here is we've got some really nice data. So we've got the ventilatory data here. So, and then we've got our VO2, this is VO2 max data here. This is the ventilatory data. This is maximal lactate steady state. And then, so that's at a much higher workload. And this is the lactate data. This is the lactate turn point data. So ventilatory and lactate data should confirm. Remember, physiologically, they should confirm. So if we look at the data across the participants, and here's the thing, you've got no data, because again, it's quite hard to get blood lactate sometimes. So here we go. 15, 15, 14 and a half, 15, so slightly out, 16, 16, 15 and a half, 15, slightly out, 15 and a half, 16, slightly out, 15 and a half, spot on. Just out, no data, out by half, This is quite a big one that's out here. But the average is basically a difference of 0.2 of a kilometre. Now, remember, you know, you're going, well, look, they're not absolutely spot on, but remember that the Gaskell work is saying, look, as long as there's less than a kind of a 3% difference between workloads, then we've got agreement. And my advice would always be, you may go, well, hold on, which is correct, Dan? Is it the lactate data that we use to identify aerobic capacity, or the ventilatory data? Remember that you're going to identify this now. You're going to identify this in 3 ways. You're going to identify it using the lactate response, the V-slope, and the ventilatory equivalence. You go with the 2 that absolutely agree. If there is a disagreement like they've got here, so let's say that you've got this one here, 15 and a half and 15, you now corroborate the ventilatory data with the V-slope and the ventilatory equivalence. If that is where the disparity lies, then I would go to the lactate data to identify it. Please note, though, that in most cases, not all, but in most cases, you will see that the maximal lactate steady state is at a higher workload than the lactate turn point. And that's really important, because remember what we said earlier on, that maximal lactate steady state represents that workload beyond which you lose metabolic control. It's connected to the end of the zone of isocapnic buffering, so it should be at a much higher workload. Okay, and then they've got some correlational data here as well, which is correlating things like the velocity of maximal lactate steady state. So this doesn't necessarily help because it doesn't give us cause and effect. But here you've got the velocity at the they call it ventilation. This is gas exchange threshold, correlated to the data, what they call the lactate minimum. Remember, be slightly cautious. Lactate minimum is not a reliable indicator of the lactate turn point. But if you take the velocity here at lactate, I'll try again. If you take the velocity here at the ventilatory threshold, it's got a reasonably powerful correlation to the lactate minimum data. And if you correlate it here to the data at lactate turn point, it's still reasonably strong. It's still got a correlation, which one would accept as being an acceptable correlation. So this is from Maya, and I kind of want to use this to kind of conclude this section before we move into the kind of the next part. And they write this: the workload at VT, remember they're just using ventilation, remember, just don't get confused, lots of abbreviations, gas exchange threshold, represents the first rising lactate concentrations during incremental exercise. It's the big rise. Remember, there is an initial increase, but it's not a big rise, which is LT1. Unfortunately, many researchers have not correctly detected gas exchange threshold because of inadequate test protocols or because they have mistakenly picked up the respiratory compensation point, which is where we're going to go to next.